Texture quality. Texture quality controls how detailed every surface looks in your game. The stitching on a jacket, the cracks in a wall, the grain on a wooden sign. Look at this Witcher 3 comparison. At Ultra, every carving on that signpost is sharp and readable. Drop to high, still solid. Hit medium, and the detail starts dissolving. At low, the wood looks like painted plastic. Same object, completely different reality. The strength here is simple. Higher textures make your game world believable up close. No other setting has this level of immediate visual impact. But texture quality is the most VRAM-hungry setting on this list. Ultra textures in Cyberpunk 2077 alone can exceed 8 gigabytes of VRAM. When your GPU runs out, it borrows from slower system RAM, and your frame rate collapses. For anyone on a 4 gigabyte or 6 gigabyte card, Ultra isn't an upgrade. It's a liability. Anti-aliasing. Anti-aliasing is a feature that smooths out jagged edges on objects in your game. It was introduced in the late 1990s as 3D gaming went mainstream. The problem it solves has a name, aliasing, and it happens because every game is built from square pixels trying to draw diagonal lines. Squares can't make smooth curves, so without help, every edge in your game looks like a staircase. Watch this GIF. Look at the tower, the roof lines, the tree branches. And with anti-aliasing off, every diagonal edge is broken and harsh. The moment it toggles on, those same edges become clean. Same scene, completely different finish. The strength is polish. Anti-aliasing makes any game look more expensive than it is, especially on thin objects like fences, wires, and branches, where aliasing is most brutal. The trade-off is performance. Higher AA methods like MSAA can cost you 10 to 15% of your frame rate. For competitive players, that's a real sacrifice. HDR, high dynamic range, is a feature that expands the brightness and color depth of everything on screen. Without it, your display picks one exposure and commits. Bright areas blow out, as dark areas crush to black. You lose detail at both ends. Look at this comparison. The SDR side, the rocks in shadow are barely visible. The sky is overexposed. Switch to HDR. The same rocks now show full texture, and the sun still holds detail without blowing out. That's not a filter. That's your GPU and display working together to show you information that was always there. The strength is realism. HDR makes dark scenes readable and bright scenes believable at the same time. Your monitor has to support it. Enable HDR on a non-HDR display, and the image actually looks worse. Washed out, low contrast, almost gray. Display sync. Display sync is the technology that fixes screen tearing, a visual glitch that happens when your GPU and monitor fall out of sync. Look at this screenshot. See that horizontal split cutting across the middle of the screen? That's tearing. Your GPU finished a new frame and pushed it out before your monitor finished displaying the previous one. 2 frames, 1 screen, at the same time. The first fix was V-Sync. It forces your GPU to wait for the monitor before sending a new frame. Tearing gone. But that forced wait introduces input lag, and in fast games you feel it. So Nvidia built G-Sync and AMD built FreeSync. Instead of forcing the GPU to wait, these technologies flip it. The monitor dynamically matches the GPU's output in real time. No tearing, far less lag. G-Sync and FreeSync both require a compatible monitor. Without one, you're back to choosing between tearing or lag. Dynamic resolution scaling. Dynamic resolution scaling is a feature that automatically lowers your game's resolution during heavy moments to keep your frame rate stable, then raises it back up once the load clears. Look at the first comparison. Same hardware, same scene. 60 frames per second with dynamic resolution on, 34 frames per second with it off. That's not a minor difference. That's the difference between smooth and slideshow. Now look at the second image. Dynamic resolution off, sharp, detailed. Dynamic resolution on, slightly softer. That softness is the trade-off. Your GPU is intentionally rendering less to stay above your FPS target. The strength is consistency. In open-world games where one heavy scene can tank your frame rate, HDRS acts as a safety net. You trade a little sharpness for a stable, uninterrupted experience. In slower cinematic games where image quality matters more than frame rate, the resolution dips become noticeable and distracting. Anisotropic filtering. Anisotropic filtering is a feature that keeps textures sharp as they stretch into the distance. Without it, surfaces that extend away from your camera, roads, floors, the long corridors go blurry the further they get, even if your texture quality is maxed out. Look at this comparison. No AF on the left. That road starts losing detail just a few meters ahead and turns into a muddy smear by the time it reaches the distance. 16 times AF on the right. The same road stays sharp and readable all the way to the horizon. The strength is impact versus cost. When anisotropic filtering at 16 times produces a dramatically sharper image with almost zero performance hit. The weakness is invisibility. Most people never touch this setting because the difference only shows on surfaces viewed at a steep angle. Leave it on auto and you're leaving visible quality on the table for free. FSR, FidelityFX's super resolution, is AMD's upscaling technology that renders your game at a lower resolution and then uses algorithms to reconstruct it back up to your target resolution, reducing the workload on your GPU in the process. Look at this comparison. Native on the left. Every hair strand, every skin pore is crisp and defined. FSR 2.0 on the right. The overall image holds up well at a glance, but look closely at the hair and beard. The fine detail softens when that reconstruction is doing its best, but it is not the real thing. Unlike DLSS, FSR works on every GPU, Nvidia, AMD, and Intel. If you're on older hardware struggling to hit your target frame rate, FSR gives you a meaningful performance boost without locking you to one brand. The weakness is quality at lower FSR modes. Set it to performance or ultra performance, and that softness becomes impossible to ignore. Ghosting on fast-moving objects, smearing on fine details. Frame generation. Frame generation is a feature that inserts artificially created frames between real rendered frames to boost your FPS counter and make motion feel smoother. Look at this comparison. Default rendering, 53 frames per second, 44 milliseconds of latency. DLSS frame generation, 85 frames per second, but latency jumps to 59 milliseconds. The frame count goes up, but so does the delay between your input and what you see on screen. Watch the bullet position across both panels. Same moment in time. The bullet is further along in the default render. Frame generation is showing you a slightly older version of reality dressed up as smooth motion. The strength is cinematic experience. In slow-paced story games where you want fluid, film-like visuals, frame generation delivers a genuinely smoother feel with no extra GPU rendering cost. The weakness is that latency increase. In any competitive game where reaction time matters, while 59 milliseconds of input lag is not a cosmetic issue, it will get you killed. DLSS, Deep Learning Super Sampling. DLSS is Nvidia's AI-powered upscaling technology introduced in 2018 that renders your game at a lower resolution and uses a trained neural network to reconstruct it at your target resolution. Look at this comparison. Native 1080p on the left, DLSS quality mode on the right, same output resolution, but the GPU is doing significantly less work on the right side. At a glance, the two images look nearly identical. The palm trees, the rooftops, the distant cityscape, DLSS holds up remarkably well across the whole scene. The strength over FSR is intelligence. DLSS doesn't just upscale, it uses temporal data from previous frames to reconstruct detail that wasn't even rendered. In quality mode, most people genuinely cannot tell the difference from native. Ultra DLSS only works on Nvidia RTX cards. Ray tracing. Ray tracing is a lighting technology that simulates how light actually travels in the real world, bouncing off surfaces, casting accurate shadows, and producing real reflections instead of faked ones. Look at image 1. RTX off. The water is flat, generic, disconnected from the scene above it. RTX on. The entire structure above is accurately mirrored in the water. The light knows where it came from. Now image 2. RTX off. That glass wall shows a blurry green approximation of a reflection. RTX on, the exact character standing behind you appears correctly in the glass. Same position, accurate angle, real geometry. In scenes built around reflective surfaces, water, glass, and wet roads, ray tracing closes the gap between game and reality in a way no other setting can. Ray tracing is one of the most GPU-intensive features on this list. In competitive games like Fortnite, enabling it can cut your frame rate by 40% or more. For casual players, that's a trade-off. For competitive players, it's a non-starter. Path tracing. Path tracing is the most advanced lighting technology available in games today. An evolution of ray tracing that calculates light for every single surface in a scene simultaneously, not just selected reflective ones. Look at image 1. Rasterization on the right. The helmet is flat, lighting is approximated. Ray tracing in the middle. Reflections appear but only partially. Path traced on the left. Every surface, every angle, on every reflection calculated with full accuracy. Now image 2. Ray tracing handles the mirror and sphere, but the room still feels staged. Path tracing. The green light bleeds onto the white walls. The purple spills across the floor. The entire scene breathes like a real physical space. In supported games like Cyberpunk 2077, path tracing produces images that genuinely blur the line between rendered and real. When path tracing demands so much GPU power that even an RTX 4090, Nvidia's most powerful consumer card, requires DLSS just to stay above 60 FPS at 4K. NVENC, Nvidia Encoder, is a dedicated hardware chip built directly into Nvidia GPUs that handles video encoding for streaming and recording, completely independent of your CPU. Look at this comparison. CPU encoding on the left. The zoomed crop is blurry. Detail breaks down. The image compresses poorly under the load. On the right, sharper, cleaner, more detail preserved. Same bitrate. The dedicated chip simply does the job better. CPU encoding pulls processing power away from your game to compress video in real time. Your FPS drops, your game stutters. NVENC handles the entire encoding workload on a separate chip inside the GPU, leaving your CPU and frame rate completely untouched. NVENC is locked to Nvidia RTX cards only. AMD and Intel GPU owners have their own encoder equivalents, but NVENC remains the industry benchmark that streamers on Twitch and YouTube measure everything else against.